Global warming potentials, emission factors, and carbon versus carbon dioxide. The greenhouse effect. As you probably already know, the Earth receives energy from the Sun in the form of solar radiation. About 50% of that radiation is absorbed at the Earth's surface. The remaining 50% is reflected back into the atmosphere in the form of infrared radiation, or heat. The greenhouse gases discussed in the previous lesson trap this outgoing infrared radiation in the atmosphere, thereby heating the Earth. Therefore, the more GHGs are present in the atmosphere, the warmer the Earth becomes. This process is known as the greenhouse effect. Global warming potentials. Different greenhouse gases trap heat in the atmosphere at different rates, and they also have different atmospheric lifetimes. This raises the question, how do we make meaningful comparisons between gases? In order to get around this problem, scientists use carbon dioxide as a benchmark for measuring the heat-trapping ability of each of the other greenhouse gases. Furthermore, to resolve the issue of different atmospheric lifetimes, a time span of 100 years is typically used in evaluating a gas's heat-trapping effect. A gas's heat-trapping ability, measured against carbon dioxide over a fixed time period, is known as its global warming potential. This chart shows the global warming potential of each of the 6 GHGs. For example, methane has a global warming potential of 25. This means that methane is 25 times more potent than carbon dioxide. In other words, emitting 1 ton of methane into the atmosphere has the same warming effect as emitting 25 tons of carbon dioxide. As you can see from the chart, HFCs, PFCs, and sulfur hexafluoride are extremely potent greenhouse gases. The EPA refers to these gases as high global warming potential gases. In fact, sulfur hexafluoride has nearly 24,000 times the heat-trapping ability of carbon dioxide. Note that since carbon dioxide is being used as a benchmark, by default, its GWP is 1. For more information about how each gas's global warming potential is determined, follow the links below. Carbon dioxide equivalents. When calculating the warming effect of a specific batch of gas, the result is expressed in a unit called carbon dioxide equivalents, which is written as CO2e. The unit's name reflects the fact that a gas's warming effect is always measured against carbon dioxide. The use of a common measuring unit for all gases enables us to make comparisons between gases. A corresponding example is that in economics, we would measure a country's gross domestic product in dollars, even if that country doesn't use dollars as its own currency. This allows us to compare the size of 2 economies that use different currencies and engage in different economic activities. Similarly, in GHG accounting, the total effect of a batch of gas is expressed in carbon dioxide equivalents. To calculate the warming effect of a specific batch of gas, we simply multiply the gas's GWP by the quantity of gas present. For example, let's compare the warming effect of 1,000 tons of methane and 100 tons of nitrous oxide. Methane has a global warming potential of 25. So, 1,000 tons times 25 equals 25,000 tons of CO2 equivalent. Nitrous oxide has a global warming potential of 298. So, 100 tons times 298 equals 29,800 tons of CO2 equivalent. As you can see, this means that emitting 100 tons of nitrous oxide has a greater effect than emitting 1,000 tons of methane. This comparison is made possible by the use of CO2 equivalents as a standard unit of reference. Carbon versus carbon dioxide. Next, we're going to take a look at the difference between carbon and carbon dioxide. People often use the term carbon emissions to describe the release of carbon dioxide into the atmosphere. This can be somewhat misleading because it's carbon dioxide, and not carbon, that is a greenhouse gas. The following example explains the difference between carbon and carbon dioxide by examining the combustion of gasoline. Here we go. 1 gallon of gasoline weighs approximately 6.2 pounds. We also know that gasoline contains 85.2% carbon by weight. This tells us that 1 gallon of gasoline contains about 5.3 pounds of carbon. But when gasoline is combusted, oxygen molecules combine with the carbon to form carbon dioxide. You may remember from chemistry class that the atomic weight of carbon is 12, and the atomic weight of oxygen is 16. Thus, the combined weight of one carbon atom and 2 oxygen atoms is 44. So, the ratio of carbon to carbon dioxide by weight is 12 to 44. In other words, carbon dioxide weighs 3.67 times as much as carbon. So what does all this mean for our gallon of gasoline? Well, what started out as 5.3 pounds of carbon in the gallon of gasoline turned into 19.37 pounds of carbon dioxide after combustion. Similarly, what was initially 1 gallon of gasoline resulted in 172 cubic feet, or the volumetric equivalent of 1,286 gallons of carbon dioxide. This is because the carbon atoms combine with oxygen atoms from the atmosphere during the combustion process to form carbon dioxide molecules. Consequently, every gallon of gasoline that is combusted, whether in a semi-truck or a Toyota Prius, will result in 19.37 pounds of carbon dioxide emissions, with no exceptions. End of recording.